Welcome to the third lecture of the Cognition and Intelligence course. In this lecture, we're going to be talking about sensation and perception. I was kind of late to the lecture, so I don't know what he was saying about these three things that are on screen right now. But I know we're going to talk about perception in this lecture, which is the psychological processes that happen in your brain that kind of help you to make sense of the universe. There are a couple of different types of perception or different ways that your mind figures out the world around it, and I'm going to talk about a couple of those now. The first is visual accommodation. And that's very basically an awareness of how much the muscles in our eyes are moving in order to focus on an image on our retinas. So the lenses in our eyes work by muscles in the irises expanding and contracting and so on. And then it changes the curvature of the lenses in our eyes that keep an image sharply focused on our retinas. At some level, our brains process informations on how much those muscles are moving in order to make those adjustments in our eye lenses. So that tells us how much work we have to do to focus on something. The closer something is, the harder our muscles have to work in order to focus on it. Another cue that we take from the environment relying on two eyes is called retinal disparity. So if you take your pen and you hold it out in front of you, and you close one eye, then you close another eye, you close your one eye, you close another eye. I hope you're doing that with me. It kind of looks like the pen is jumping about. It looks like it's moving, but it's not, because your hand is staying still. What's happening when you have both your eyes open, you see one pen. But when you swap between the eyes, it kind of looks like there might be two of them. What's happening is that your brain is making sense of the information that it's receiving from both eyes separately, and it's integrating that information into one image. So you only see one picture rather than two pictures. Each of your eyes is obviously slightly in a different position because they're not in the same place on your head. So there's a spatial difference between where our eyes are. So we get slightly different spatial pictures of the stuff that we look at, but the brain makes sense of both of them and interlinks them. If you try the same thing with the pen and put your arm out a little bit further, there's a smaller jump in distance, and if you bring it closer, it's a much bigger jump in distance. That's your brain making sense of the disparity between your two eyes, and that's how it calculates how close or how far away things are. The other thing that your brain does, binocular cue-wise, and you can test this yourself if you put the same pen in front of you and bring it closer towards you slowly, everything kind of goes a bit squint. That's called convergence. The muscles that move your eyes around and help you focus on stuff are being monitored by the brain. Brain is monitoring how much you move your eyes, and based on a sense of how much it takes to focus on something that you're looking at, your brain calculates how far away that thing is from you. So that's how your brain makes sense of the physical features of stuff that we get from the environment. It's a bottom-up process, depth perception. But there's other ways that we make sense of visual information that are psychologically driven. Usually these are related to perceiving shapes and form perception. The ways in which we group bits of information together in order for them to make sense to our vision. What we tend to do is use a bunch of principles for organizing information that are referred to as Gestalt principles. That's a German word. It means the whole thing. So what we tend to do with visual perception is we tend to perceive entireties or wholes rather than individual parts. So if you look at this little slide, you can see examples of that. There's a number of Gestalt principles that we use in order to make sense of things. The first is called figure ground principle. So if you've ever seen that, like there's some optical illusions where you have to see like one thing or another thing, like in class we saw the figure faces in the vase, where you can't concentrate on both of them at the same time. You have to see just one of them. I don't have the picture here, but if you were there, you'll remember it. You can Google it too. Either you see the background as being the black with the vase in the foreground, or the faces in the foreground with the white background. But we can't look at both of them at the same time. That is one of the Gestalt principles. Another Gestalt principle that we tend to use is the idea of proximity or nearness. So if you look at the pictures with the arranged dots, we tend to interpret that information in particular types of ways depending on how close the dots are to each other. So in the one you see vertical lines because we organize that information in specific ways because they're close together vertically rather than horizontally. But the one on the right, they are horizontal. You see horizontal lines of dots because the horizontal ones are closer together. In the middle one, you may kind of see like little squares or whatever. There's no real closeness. We have a perceptual tendency to group things together based on how close they are in the space. We also tend to group things together in terms of similarity. So if you look at the two pictures in the middle, you kind of will see two triangles rather than a six-pointed star made out of dots, because we group the like ones together, the white ones together in a triangle, the black ones together in another triangle pointing up, hoping that you're following me. On the left is the principle of continuity. So when you look at that kind of XY thing, you kind of go from the top left corner to the bottom right corner. So you see an X of dots. You don't really see it going from top left to top right as like a little curve. You rather see two straight lines intersecting. That is the principle of continuity, that the lines continue straight. So we have a whole bunch of principles that we tend to use to group visual information. The last one that we tend to use is called closure. And you can see that in the pictures at the bottom. What we tend to do with partial stimuli is we will complete the picture in our minds. So in figure A, you'll see a white triangle rather than three circles that are incomplete. You see a white triangle superimposed in front of three black circles. In the next picture, you see a kind of thing wrapped around a white cylinder or rectangle rather than little quotation marks. In the one at the bottom, you see a sphere, a little white ball with spikes. And the last one, you kind of see a little wormy or a Loch Ness monster type thing rather than just the lines. So on the basis of partial information, we tend to complete things. We tend to assume that they are whole. But that assumption isn't entailed in the information that we're getting. It's a psychological feature of our perception. It's top-down, conceptually driven. So perception can work in both ways, data-driven and perceptually driven. For the rest of the lecture, we're going to talk about attention. It's really important for cognition and thinking. We're going to go back to it when we talk about memory at some point. But when we talk about attention, there is still an underlying idea that attention can be either data-driven or conceptually driven as a process. How we go about deciding what we're going to pay attention to depends on whether or not the information that we get is of a certain kind or if it's important to us. And we can only decide if it's important to us by processing it conceptually. So, attention really means focus. focusing, our sensation, and our perception. It means attending to the features of sensory information. And it happens in both those ways, bottom up, in terms of driven by data, and top down, in terms of psychologically driven. So when we talk about bottom up or data driven attention processes, we're really talking about the neurological level. You know how nerves work. Sense impulses have to be a certain strength for a neuron to fire. So on the basic neurological level, the information that we get from the environment has to be intense enough to impinge upon our sensations and our awareness for us to pay attention to it. So, as an example, if you're just talking in a room and people are chilling, you're not really going to concentrate on other people's conversations, you're not really going to pay attention. But if someone starts talking suddenly very loudly, you are going to pay attention. The information that's in your environment is actually reaching your awareness, data-driven wise. It impinges on your senses, it actually gets to you. Psychologically, we're talking about conceptually driven or top-down. The information from the environment has to be important to us, not just loud enough or bright enough or strong enough. It needs to be important enough for us to pay attention. The stuff we're not interested in, whether or not it's said in a loud way, or whether it's colorful or it's bright, if we're not interested, we're not going to pay that much attention to it. And the decisions that we make based on what we decide to pay attention to are usually focused on our own personal perspective of the world. So it's commonly accepted that attention is under our voluntary control to some degree, particularly the psychological determinants of attention. We choose what we want to pay attention to. So for example, if you're in a lecture and the lecture's boring, you're not really gonna pay attention. Because your attention is under voluntary control, you decide what you want to focus on. Attention is selective. The other thing we know about attention is that we seem to have a limited capacity for attention. We battle to process different things at the same time. You can't focus on driving and texting. There's a problem in that we do have to focus at some point on what we have to pay attention to, because we don't have enough attention to go around. It's a basic defense mechanism. It stops your brain from overheating, because there's so much going on in your environment at any one time that if you were to try and focus on everything, you wouldn't be able to focus on anything. So we do have a filter. There's a limited capacity for our attention. And it's commonly understood as a bottleneck. There's lots of information coming in, but we can only focus on some of it at any given point in time. And there's a couple different theories to account for where that bottleneck occurs and how we process information in relation to that. So for the rest of the lecture, I'm going to talk about a couple models for how attention works. The first is called filter theory. Second is attenuation theory. And the third is the distinction between early and late selection. All three of these models of attention argue that there is some point in our processing of information where we have to make a decision about what we're going to pay attention to and what we're going to ignore. So let's look at filter theory. Filter theory was developed by a researcher by the name of Broadbent. Broadbent argues that there are multiple information channels that impinge on our awareness at any given point, and we need to make a distinction between them. The way we choose between those information channels is by their characteristics. we make a distinction between different types of information based on the features of that information. So we have a selective filter for information, filter theory. So we decide at some point what we're going to focus on, what type of information is important and what's not important. And that filter tends to be first person focused, and it also tends to be about the physiological features of that information. If there was suddenly a bright light, you'd you'd look and try and shield your eyes or whatever, but you would react, you would focus on it. So sometimes our attention is swapped very quickly by the features of the information that come through. Strong sensory input is usually prioritized. You can argue that that's an evolutionary adaptation. Broadbent shows that this happens through what he called the dichotic listening task. So people get a set of stereo headphones in this task, and he played one message to the left ear and one message to the right ear, different messages. So in the listening task, it's a very simple task. A sequence of numbers was read out in the left ear and a sequence of numbers in the right ear, 3 numbers each. One set to the left ear and one set to the right ear. What the research participants had to do was repeat all 6 of those numbers. So they had to repeat those numbers in 2 ways. Firstly, they had to repeat what they had heard in the left ear and then in the right ear separately. And then they had to repeat the numbers by pairs. And that was a lot more difficult. Why? Because in order to repeat them pairwise, you have to switch your attention back and forth between the 2 ears, let's say. So you have to focus first on the left, then on the right, then on the left, then on the right. Broadbent argued that multiple switching costs attention, whereas focusing just on one ear and then on the other, you only have to switch once. When you focus on pairs, you got to switch a couple times, and that costs attention. So it's easier to do the ear-by-ear task than the pair task, because there's a cost to switching your attention so many times. He also found that if participants were given the headphones and told to ignore what's happening in one ear, maybe focus only on the left ear, for example, it was easier for them if they repeated to themselves the signal that was coming in through the left ear. So if you're hearing the numbers and you repeat them out loud, you'll remember what's happening better. You'll discriminate better. And that effect is called shadowing. So if you're told to attend to one message and ignore another one, if you shadow the message that you must attend to, you'll remember it better. You'll focus your attention on it more effectively. But Broadbent also found that despite the cost to switching between ears, and in spite of shadowing as an effect, some participants were still able to recall both lists of numbers, one in each ear. So he argued that what we do have in our perceptual awareness is what he called the sensory memory store, which we will come back to when we talk about memory. Sensory memory store is kind of very, very short-term memory for sensory information. It's a very brief mental representation of the information that we receive in our environment. The example that he gave in class is like that kind of afterglow inside your eyes if you're looking at something and you close your eyes quickly, and there's like a kind of little after image of that thing. That is the way he describes this concept in practice, as a very brief mental representation. And that's the iconic sensory memory. So we have iconic and echoic sensory memory. But there's a little bit of an issue with filter theory. The argument is that the numbers, the two lists of numbers, is the same type of information. So it's relatively simple to distinguish between the two messages because the type of information isn't very complicated, it's not very meaningful. So a repetition of the study was done using a mixture of words and numbers in the right ear and a mixture of words and numbers in the left ear that you had to then remember. And the researchers who did that found that it's easier to do the switching if we focus on the meaning of the information and not just the information. So you focus on the words in the sentence and the numbers as meaning units in their own right. And it's easier to focus on different types of information because they mean different things. So it's not just switching on the features of the information, but sometimes we switch on the meaning of that information as well. So it's easier to do the dichotic listening task if you can distinguish between different categories of information.